This is part 4 of the tutorial about church encoding. In this part 4, I will be talking about church encodings for higher kinds or higher kinded types. Previously, I discussed church encodings for simple types and for type constructors. In most cases, that's sufficient. But in some cases, one needs church encodings for higher kinded types. That is, for type constructors, or for generalized algebraic data types, such as called JDTs. In this tutorial, I will be just talking about some cases where we need church encodings for higher kinds, and I'll show some examples. So first of all, what is that that is going to be the church encoding at the level of type constructors or higher kinds? A usual church encoding looks like this. The arbitrary type R under the quantifier is a type, is an ordinary type, is not a type constructor. So then the result C is again an ordinary type. Now we would like to use the same idea at the level of type constructors, which means that R is going to be a type constructor, and the result C is also going to be a type constructor. Now, if we don't make changes to this formula, it won't work. So let's see what changes are necessary. So first of all, F must be something that takes a type constructor and returns another type constructor. So it's a functor, which we will call F also, but it's a functor at the level of type constructors. So it takes a type constructor T or a functor T and returns another functor Ft. Second change which is necessary is that this function type fr to r, it used to be just the type to type, because fr was a type and r was also a type. Now r is going to be a type constructor and fr is also going to be a type constructor. So what is this function from one type constructor to another? We cannot write that function directly. Instead, we need to write this kind of function type from type constructor fr applied to an arbitrary type T to the type constructor R applied to the same type T. And the type T must be universally quantified. So with these two changes, we can now write down the formula for the church encoding at higher kinds. C is going to be a type constructor. So in order to define it, we need to apply it to some type A. So A is just going to be an arbitrary type parameter. The formula is that for all R, and R is now a type constructor, from this function, which we just talked about, we need to get RA, so the application of this type constructor R, which is arbitrary, to the type A that was given on the left side. So that is actually the formula for the type. It's quite complicated now. There are lots of things here which are changed and which make it more complicated to work with. But the good side of Dhall is that everything is written out explicitly. So you see what type everything has. So this has type, or kind rather, type to type. This is a function with a type parameter, and so on. Everything is explicit. So now the complexity of this church encoding is in your face. If you did something like this in Haskell, which you certainly easily can do, then these things would be hidden. You would not see necessarily that you have here a type parameter. You might have to write it in certain places, but not everywhere. So using Dhall's features, we can rewrite this formula as a general combinator, which I will denote here L fix K, for fixed point at the level of type constructors, higher kinded fixed point. It creates a fixed point type constructor, so the result of applying this to some f will be a type constructor. So it takes a type parameter and gives you a type as a result. So this, what I just highlighted right now, is a type. So this is the formula for the church encoding at the level of type constructors. So just as before, it is certainly not obvious that this formula is correct. It needs to be proved. And I'm going to skip over that. And I'm just going to go into applications and how to use this. So first condition for being able to use this is that f, the pattern functor of this church encoding, must be a higher kinded functor. So it must be covariant with respect to its argument. If it's not covariant, then the church encoding formula does not work. Just like it is the case with the church encoding for ordinary types. If you have a pattern functor f, which is used in this kind of formula for the church encoding for ordinary types, and if this pattern functor f is not covariant, then this formula is not going to work. It's going to give you a type, for sure, but this type isn't going to be the fixed point in any case. It's going to be something else, some other type, but not the fixed point of f, even if that fixed point can be defined. If f is contravariant, sometimes you can define a fixed point of or a functor that is neither covariant nor contravariant. Sometimes you can define fixed points of those functors, but they are not given by the church encoding formula. So this is what I mean when I say that the church encoding doesn't work for those non-covariant f. The church encoding formula only works correctly when the pattern functor f is covariant. So similarly, for the church encoding at the higher kinded type, we need f to be covariant in its argument. Now, the second condition which we would like to have is that p, this pattern functor, I call it p, but I should call it f here. So this is actually not quite right. So this is this should be f applied to some t and not pf. So notation mixed up. This pattern functor f must preserve functors. So if it is applied to a functor, then the result is again a functor. And why do we need this? And then if we have this, then c will be a functor. Otherwise, it won't be necessarily. So let's suppose that these conditions hold for f. I will fix this notation here. We can formalize these two conditions as a type class, kind of higher kinded functor, which says that there's an f map at the level of type constructors. So from f if you have u and v and you have a transformation from u to v, again in this sense, it's a natural transformation if u and v are functors, but actually we are not requiring that u and v are functors. U and v are arbitrary type constructors, so we don't require that this function be a natural transformation. Then you can map from fu to fv, again in the same sense. So This is equivalent, or this is analogous to fmap for functors, except this is at the level of type constructors. And second condition is that if you have a functor type class evidence for some u, then you have a functor type class evidence for fu. Now, similarly to the fix and unfix, we can write down definitions of the higher kinded fix and unfix, which show that the type constructors f of L-fix kf and L-fix kf are equivalent at the level of type constructors. So for any type A, if you apply these type constructors to A, the two types are going to be isomorphic. And the isomorphism is given by the two functions, fix k and unfix k, in the two directions. So this is the code of these functions, which is quite analogous to the code of ordinary fix and unfix, except for a bit more type parameters, as is when it's necessary. And again, I just want to mention that it's not obvious why these functions fix and unfix are inverses to each other. These functions map one type to the other and back, so the types are right, but it's far from clear why these functions are actually not losing any information, why the transformation between these types is an isomorphism. That requires a proof, and this proof is not easy, and I don't think it's written anywhere. So I have in the appendix of my book, and by the way, this entire tutorial now is converted into a book, which you can get here, if you feel like. In the appendix of this book, I show the proofs for ordinary church encodings. For instance, why fix and unfix are inverses to each other for the ordinary church encoding. That proof is long enough. I suppose that quite a similar proof would work for type constructors if you put in enough lambdas. But I did not try to do that, so I just expect that to work. So here's an example. Let's write a list functor in terms of the higher kind of church encoding. List functor is a functor, right? So previously we defined the list functor using an ordinary church encoding by the trick that we fix the type parameter as if it's a fixed type, and then we can use an ordinary church encoding. But we don't have to do that if we have the higher kind of church encoding. So let's write down the equation for the list in this form. So T is the list type, and then TA is equivalent to this, the optional of pair of A and TA. That's equivalent to the definition of list, the recursive definition of list. But now it is formulated in terms of higher kinded types. So F is a higher kinded functor, and if we write it like this, then this is essentially T equals FT. And FT is defined like this. So then we just use this combinator L fix K on this functor list Fk. So this is list Fk. In Dhall, we define list Fk, and then the functor instance, this higher kinded functor instance, which is fairly straightforward to define. And we're done. So here we have the higher kinded list encoding. And this should be sufficient to define lists, shouldn't it? Now, it turns out that, well, first of all, the curried form is actually longer because you need to duplicate the universal quantifier, but no matter. Let's try to work with this list in this encoding. And we'll find very soon that there are issues. Here are the constructors. So we construct a nil empty list. Cons is the usual cons. Now you see they all have a lot of type parameters. Well, that's okay. So here is how we construct the first example. A list 1, 2, 3. We need to put a natural everywhere. And just as before, it's not really very different from the previous constructors. So that's fine. Looks like we're done. But, okay, so we can actually convert to the ordinary list and fold using a foldable instance, which is the same as just being able to convert to list. And yes, indeed, this folds to 1 to 3. Looks like it's very good. And actually, for list, we didn't have to use a higher kind of church encoding, but there are types for which we do have to use it. And these types are called nested recursive types in the type theory literature. And I give an example of that. An example of that is perfect tree. It's a tree-like data structure, but the branches are such that at every level there's exactly 2 branches except for the last one. So there must be, in a perfect binary tree of depth n, exactly 2 to the n leaves. So it's a perfectly shaped binary tree. It can only contain exactly 2 to the n leaves for n equals 0, 1, 2, and so on. So this is a definition of the perfect tree in Haskell. And you see that what happens is it's either a leaf or it is a branch where we use the same data type on the pair. And because of this, the same data type will be either a leaf, which means it will be a pair, or it will be a branch, which will be a pair of pairs, and so on. So in this way, we can construct values of this type, and they will always look like this. Branch, 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 and then leaf, and then a big nested pair of pairs of pairs of pairs, and so on. So because this is always constrained to be of this shape, it's always pairs of pairs of pairs, that's why the perfect tree can only contain 2 to the n leaves. And if you don't put in the correct number of tuples, it won't type check. So it is constrained at type level to have this shape. So this is a tricky type, which is not easy to work with, because, as you see, the recursive definition of this type defines PB3A in terms of not PB3A, but PB3 of something else, of a pair AA. And so you cannot write this recursive definition by saying, let's put A to some fixed type, set A to some fixed type, and call this R, and then you will have branch of RR or something. This is not RR. This is not expressible through PB3A. It is PB3 of something else. And this something else is nested under the recursive call of PB3. That's why they're called nested types. Although it's not particularly illuminating. But that is the terminology. So how do we define that? Now, we cannot define this if you can, in the usual way using the ordinary church encoding, for the reason I just explained. And if you compare this with the list definition, list A is defined in terms of list A, but PB3A is not defined in terms of PB3A. So we must use a higher kind of church encoding for this. So the pattern functor f needs to be applied to the PB3 type constructor itself. It is a new type constructor that takes a type parameter A and applies PB3 to the pair AI. So this is how we need to write the definition of the pattern functor. And this is the definition that requires us to have R of type, of kind rather, type to type. So this then is the definition of the pattern functor R, pattern functor F. It is a pattern functor at the level of type constructors. It takes a type constructor R and gives you another type constructor, which is take A and return some type. So this is what we call here a pattern functor on the level, at the level of type constructors. And if we put the church encoding that we just saw to work, we can define PB3 like this, with this pattern functor. Constructors can be defined and sample values can be defined. So here I'm using the pair, and pair is something we define in Dhall for convenience. It's not built into Dhall. But now notice how many type parameters we have to write. Here is a type parameter, here's another type parameter, here's another type parameter, and then these are all these pairs of pairs. So this is just level 2 with 4 leaves, and this is how verbose it becomes. But this is the price. You have full type safety. Dhall does not have type inference, so you have to write down the entire set of types by hand. Nevertheless, we can work with this type and we can convert it to list, so in the order, and just to make sure that we have the right data. So we make it foldable. We can compute depth, so we can define a function that computes depth. And we can define a pretty printer. So this is again a fold of some kind. So now let's look at this example. So how do we implement a pretty printer for the perfect tree? We need to convert it to text. So we need a function of this type. Let's suppose A is a type that has a show type class instance. And now, how do we convert this to text? Now we can apply the value tree of this type to some parameters. But to what parameters? If you look at the type of the higher kind of church encoding, then first parameter is this arbitrary type constructor R. So let me look again at where it is. The higher kind of church encoding here. So it's the arbitrary type constructor R, and then this function. So we need to give these two parameters. We need to find some type constructor R, a specific one, such that the result of type RA is what we want to compute. Which means, by the way, that typically we would need to compute a result of a generic type, not just a specific text or natural, but we will have to compute a result of some type constructor applied to an arbitrary type parameter. That is what we can do with this higher kind of church encoding. So this is actually a problem. How to choose this R such that RA is the result we want, the type of the result we want. If we want to obtain text, then can we just choose R as a constant type constructor that always returns text, ignoring the type A? Maybe. It depends. In this case, for the perfect tree, and for the perfect tree that works. So we define p as a constant functor that ignores its argument, always returns natural, and then the result is of type PA, which is always natural. So that's good. And for the pretty printer, it turns out we cannot do that. It turns out that we need a instance of show t in there. Not just return text, but return a function from show t to text. Otherwise, you won't be able to print, it turns out. How do we see that? Well, what if we choose p as a constant functor that always returns text? But we need to supply a function q of this type. And this function would be then of this type. For arbitrary s, we need to convert this to text, and we cannot. The leaf value has an arbitrary type s, so we don't know how to convert it to text. We don't have a show evidence for s. We have a show evidence for a, but not for some arbitrary unknown type s. However, we're required to produce this function. So that's why the constant functor doesn't work in this case. So what other functor would work? After some trial and error, let's think about it and see, well, this is actually the type signature equivalent to this one if p were this type, if PA were this type. So then it turns out this works. So we take p as this type constructor that takes a type t and returns a type of functions from show t to text. And then it turns out we can supply this q for all s, because show s will be given. And then we have a pair of ss. So we just need to show how to write code that supplies the show evidence for pair, given a show evidence for a single value. And that's exactly what we can do and what we need to do to print out the perfect tree. So that is how it works. So now in this example, we see that actually it's not trivial to work with these these values in the higher kind of Church encoding. We have to choose parameters, and sometimes it's not obvious what parameters to choose. It is more difficult in any case than to work with ordinary Church encoding. But it's interesting. It shows us the price of more flexibility. So the higher order Church encoding can encode pretty much anything, but the price is it would not be easy to work with that. And an example of how things just don't seem to work at all is, suppose we have a list of natural values and we want to compute the sum of the elements of that list. And it turns out I didn't figure out how to do it. I couldn't figure out how to do it with this Church encoding. That's pretty interesting. So if we try to, again, we try with a constant functor. So the first question is, what is this arbitrary type constructor R that we need to substitute? Well, what if it's a constant? Then you need to supply this kind of function, which is from arbitrary x of type t and arbitrary natural number, you need to give a natural number. But I cannot convert t to natural number. It's an arbitrary type. So I don't know how to do that. When the list of type natural is constructed, the type parameter t will be actually set to natural, but we don't know this in this function. So we cannot check that t is natural. T must be arbitrary in this function. And that's why this doesn't work. Now, what else works? Well, let's try a trick like we did for the pretty printer. So let's add some stuff to the type signature of R. So what kind of stuff do we need? Well, it must, so what is that? Let's see, some functor f that we, again, this shouldn't be called f because, well, let's call it f anyway. Let's call it f, it's okay. So what kind of f can we choose so that this conversion function can be implemented? Actually, this is the core of the problem. The higher kinded church encoding makes it easy to implement functions of this type for all a from the higher kinded church encoding type constructor on a to some other type constructor on a. If you want to implement this, you just substitute f as the type constructor parameter in the higher kinded church encoding. The first argument is a type constructor parameter. And then it remains to implement this function, and this function must have an arbitrary type in there, and then you're done. So this is a bit similar to the working with the ordinary church encoding, where in order to get the value of type R, you put R as a type parameter into the encoding, and then you get the result. However, what would be this f? Now, we need to supply functions of these types, this and this. So we need to be able to construct an empty result of type ft, and given a t and ft, we need to again construct a new result of type ft, somehow accumulating all together. What kind of f is it that has these operations? Well, it has a constructor from nothing, and it has a constructor from t and from another value of that type. That's the list constructor. List can be constructed as empty from nothing or from a value and the previous list. So the most general such f is actually list t. So that means we need to implement a helper function that will do this. So we convert this higher kinded list to an ordinary list. But we already have that function. That is a higher kinded foldable. And so, of course, once we convert to an ordinary list, it will be easy to compute the sum of elements. But this is an interesting warning sign. It means that in order to perform aggregation computations with higher kinded church encodings, you need to convert them first to an ordinary church encoding. But, okay, well, when can we do that? Well, actually, for lists we can do that because we have an ordinary church encoding for lists. For perfect trees, we cannot do that. There is no ordinary church encoding, non-higher kinded church encoding for perfect trees. So this is a bit disappointing and the warning sign. So that means that it's actually harder to work with higher kinded church encoding, and it doesn't give you much more than the ordinary church encoding if it exists. So in fact, if the higher kinded church encoding is created from an ordinary one, then we can convert back automatically. So this is a combinator that takes an arbitrary bifunctor and creates an ordinary church encoding. So from L-fix k to L-fix t. I will skip the details, but essentially you can do it in general. You can use fix, and you can always just convert the higher kind of church encoding to the ordinary one if the ordinary one exists. But it doesn't exist for some types, such as the perfect binary trees. So how do we do that? So let's say we wanted to add all the numbers in some data structure, and with coefficients that depend on the position of those numbers in the data structure. So converting to list is not enough. We need a structural fold. how do we do that? So I came up with a new, more complicated construction, which I call type class constrained higher kind of church encoding. And that construction looks like this. So in addition to the usual church encoding, we say that this function, which is the argument of the church encoding, must get an extra argument of type pt, where p is some type constructor. And the idea for this pt is to provide type class evidence that the type t satisfies. So, for example, that t is some kind of number that can be added, or that t is some kind of type that can be printed, that has a show type class evidence, and so on. However, I don't know what type classes I will need when I work with this. So I keep the type class arbitrary. And that's, again, something that system f omega can do. The type class evidence, pt, is described as just an arbitrary type constructor p applied to the type t. So the type constructor p is another parameter in the church encoding. So the first parameter is the pattern functor. The second parameter is the type class constructor. And then you have the church encoding. So the church encoding will only apply to types A that have evidence of P, of type class P. So in other words, we want to only work with data that has some properties, and we build in the hooks to get those properties into the church encoding. However, we keep P arbitrary, so it's still a type parameter. So we can have trivial properties that, for example, P just returns a unit type, and every type has that property. So we can just effectively erase this if we don't need it, but we can use it if we need it. So that is the type class constrained higher kind of church encoding. And so far, now the code of this is going to be very verbose. It's going to have lots of lambdas. And here is, for example, how you construct the list 1, 2, 3. You have an arbitrary type parameter P of kind type to type, and that's a type class. And the natural type must have evidence of that type class. And I don't know what that type class is in advance. It will be determined later when I do computations with this type. So then I have the cons constructor, which is applied to P and to natural, and to the evidence that natural belongs to P. And I need to repeat this all the time. See, so it's much more verbose than before, but it works. And here is how we use this thing. So for example, suppose we want to implement a show evidence for this data structure. Then we choose P. Well, we say if P is such that A has P, and also that A has show, then this has show. So that we can implement. And then finally we apply all this. So natural has a show evidence, and so we apply this to natural and to the show natural, and then it works with, you see, it works with this example too, which has completely general type signature for arbitrary type parameters. But that's what show takes. It must take an arbitrary function of a type parameter in order for this to work. So we don't actually have show for a list. So for example 2, we don't we wouldn't have show for example 2 if the argument of show didn't have this sort of type. And this is exactly the type here. So this is the technique that is necessary. And now we can write down, for example, a general function that makes a reduce out of it using a monoid. So if A is a monoid and we have a monoid for A, and we just substitute monoid instead of this type parameter P. We substitute the type class constructor into this higher-kinded type class constraint Church encoding because it works with any type class. And now we can do monoidal computations, or we can do other things. Perfect binary tree, we can do it in terms of type class constraint encoding, just like we did before. It was going to be more verbose. And then the reduction for it is here. And then let's see, a show evidence. So it is implemented. And here is how you would have examples. So this is example 1. So we apply this with show and show natural, which means that this value, which was constructed up front, it works with arbitrary type classes and arbitrary types. So we need to pass the type class that we're working with, the evidence that our type belongs to that type class, and then we can work as if we're working more or less with a list of naturals. And then you can do things like showing naturals. So in a computation where you need to print things, then you use the type class for printing, the show type class. In a computation where you need to add things or combine things, you use the monoid type class. If you need to do more things, then you need to define a new type class, which you can always do. And then you should put this arbitrary type class instead of P here, provide your evidence, and then all you need to do is compute this function and somehow provide it. But this function would be much easier to compute because you have the type class evidence for this arbitrary type T. You have the type class evidence of the type class that you're working with. So you have operations on this unknown type, which solves the main issue, the difficulty of working with higher-kinded Church encoding. So at this point, I will wrap up this part of the tutorial. And in the next parts, I will talk about generalized algebraic data types and existential types.